Hi, my name is Tai-Danae Bradley, and I'm a research mathematician here at SandboxAQ. And for the next few minutes, I want to share with you some mathematics that my collaborator Juan Pablo Vigneaux and I have been working on. Now, this is a preprint that we've recently posted on the archive, and you can see the title on the screen. So there's some ideas in a branch of math called category theory, and this involves some work that's motivated by large language models. But rather than just jumping in and sort of telling you what the paper is about, I think it'd be helpful to have a little bit of wider context. Just to set the tone, what I'm going to share with you in the next few minutes is a little slice of a longer talk that I recently gave at the Institute for Pure and Applied Mathematics at UCLA. So if you're interested in seeing more, we'll post a link to that video below. But I just want to give you sort of a teaser. So from a high-level perspective, there's three words that I want to focus on just to kind of introduce to you these ideas. So I've highlighted them here. I want to say a little bit about categories. What does that mean? There's this word enriched here, and then also this word language. So the work that we are describing in this paper really originates from older work that I've done with some of my collaborators, which I'll share at the end, that paper. But what I really want to talk about is a mathematical framework for language that's inspired by LLMs, large language models. So here's what I mean. When I say mathematical, I really mean category theory. Now, category theory is a branch of mathematics introduced in the 1940s, so it's relatively modern. And you might say, why are we talking about category theory as opposed to any other branch in mathematics in this discussion? It's not just that we like category theory, although we do, but I hope to convince you in a little bit that it allows us to bring few assumptions to the table. So just by starting with a little bit, we can actually get pretty far, and I think that's interesting from a mathematical point of view. But I also highlighted this other word, language, or here I've said a framework for language. So how should you think about this? So what we have here, don't think of this so much as a mathematical model that we're trying to fit language into. Rather, what we're doing as mathematicians, we're just looking at what large language models have access to. Vast corpora of text, and we're just seeing what's there. We're sort of pointing and saying, what is that from a mathematical perspective? This is what I mean by a framework. So you can see it's a little different than proposing to you a model for language and trying to convince you that it's a good one. It's a little bit different than that. The other word I wanted to highlight is this word enriched. How does this fit into large language models? Well, what do they have access to? They know something about what words go with what other words in a language, together with the statistics or the probabilities of those expressions. And it turns out that this statistical information fits very nicely into existing tools in category theory. And those tools fit into sort of Category Theory 2.0. It's called Enriched Category Theory. And so I want to just give you a little taste of this in a few minutes. But these are kind of the three ideas that I wanted to highlight from our title slide. When I say categories, I mean this modern branch of mathematics. We're talking about language from a mathematical perspective. As mathematicians, we're just interested in structure and language. And now we're taking inspiration by the success of today's large language models. Okay, but I don't want to assume that you know about category theory already, although maybe you do. But I'd like to give a little teaser for this branch of mathematics in case you're not familiar with it. One way that I like to think about this subject, this is a branch of mathematics that really places a premium on relationships between mathematical objects. So here's what I mean. If you have a mathematical object like a set or a group or a vector space or a manifold or a topological space, you may want to study this object. And what you could do, you could go get a magnifying glass, so to speak, and you can kind of scrutinize your object and look at its internal anatomy and try to characterize it that way. But there's another way to understand something about a mathematical object. And that's by looking at all of the mappings out of that object or into it. In other words, all of the ways, the network of ways that object relates to other objects of its kind. Why am I saying this? How do I know that this is true? It turns out there is a very well-known theorem in category theory called the Oneida lemma. It's called a lemma, even though it's a theorem. And if you were to look up this lemma, which you can do, on Wikipedia or something, and you see this statement, it's a little bit, it's got some sophisticated words and it doesn't really look like what I'm about to say. But at the end of the day, when you kind of unwind all of the definitions, a corollary of this famous theorem is that if you want to distinguish an object, a mathematical object, from any other kind, like up to isomorphism, okay, what's the essence of this thing? This theorem says everything you need to know about that object is contained in the network of relationships it shares with other objects around it. What in the world does this have to do with language? Why are we choosing this branch of math, as I mentioned earlier? Well, it turns out there's a very similar idea in linguistics that's related to this. In the 1950s or so, there's an idea in linguistics that was introduced called the distributional hypothesis, which says, essentially, in the context of language, two words that appear in similar contexts have similar meanings. So there's this well-known quote by a linguist named John Firth, and he said, "You shall know a word by the company it keeps." So what I'm trying to explain is that something similar is true in mathematics. So I might adjust that quote and say, "You shall know a mathematical object by the company it keeps." And category theory provides a language and a tool set. It itself is mathematics, and it allows us to understand what objects are and how they relate to one another. That's what category theory is from a high level. So let me get a little bit more specific. What do I mean when I say objects? I have these blobs on the screen. So what are these blobs? Well, you can think of these as sets. I mentioned sets earlier. And a relationship between two sets is just a way to get from one to another. In other words, it's just a function. Okay. Now, I want to make a very elementary observation, and that is if I have two functions, as you see here, where the source of one matches the target of the other, then I can compose them and get a third function. In other words, two functions can compose to get a third function. Okay, that's a little bit elementary, but you'll see why I'm mentioning it in a second. So sets are examples of mathematical objects that people care about. Another example are vector spaces. So maybe my blobs are n-dimensional Euclidean space, and in that case, a relationship between two vector spaces is a function between them that respects the linear structure, i.e. linear transformations. And again, I just want to make this simple observation that if I have two linear transformations where the source of one matches the target of the other, I can compose them, and the composition of two linear transformations is again another linear transformation. Okay, what other things do people care about? Well, earlier I mentioned probabilities and statistics. Well, probabilities are real numbers in the unit interval between 0 and 1. And I can think of these as objects too, numbers between 0 and 1. And what's a relationship between two numbers? Well, there's one we're really familiar with, which is the usual ordering, less than or equal to. So here I'm just going to draw an arrow from 0.01 to 0.14 since the former is less than or equal to the latter. Now, again, we have this observation. Because this ordering of real numbers is transitive, I have this idea of compositionality again. If I have these two arrows on the left, I can sort of compose or walk along the two to get an arrow from 0.01 to 0.73. So maybe by now you can kind of see this pattern. There's some things or objects that we're interested in, and then we have a notion of relationship or mapping between them, and that mapping can be composed. There's a composition rule. And this essentially is what a category is. So I'm not giving you the formal definition, but intuitively speaking, it summarizes these examples we've just seen. In mathematics, a category consists of a collection of objects. Maybe they're sets, or maybe they're vector spaces, or maybe they're numbers. Together with relationships between them, these are things like functions or functions that respect structure in some way, things we're familiar with. Together with a composition rule, a way to compose functions when that makes sense, or these arrows or morphisms as they're called. And then you ask that this information satisfies some reasonable axioms, and we won't get into that, but it just sort of helps make everything make sense. So when I say the word category or category theory, I'm referring to this kind of formal definition that I've just explained in an informal way. So that's category theory, as a mathematician might present it. But what in the world does this have to do with language? So let's get back to language. What do we care about in language, and as in particular as we're thinking of LLMs generating strings of text sort of one token at a time? Another kind of object we could be interested in are strings of symbols. And let's declare a relationship between strings of symbols, say from some finite alphabet or some finite token set, okay? Let's say a relationship from one string to another is just that of substring containment. So I'm going to draw an arrow, as you see here, from the word curiosity to curiosity killed the cat, because curiosity as a string of symbols is contained in this longer expression. And then there's this intermediate one, curiosity sits in curiosity killed, which sits in curiosity killed the cat. So you see, in this very bare bones sense, language already fits into this nice framework of category theory. Substring containment is transitive, and it turns out when you look at the axioms that you need for category theory, it fits in quite nicely. So from a very simplistic point of view, language fits nicely into the definition of a category. Well, this is all well and good, but there's more to language than just, does this go with that? Does this expression sit in that expression, yes or no? That's just kind of a binary take on things. But of course, as we know from language models, there's probabilities and statistics. So if I say something like curiosity, intuitively you can imagine there's some non-zero probability that the rest of what I'll say is curiosity killed the cat. So what you'd really like to do is decorate these arrows or these morphisms with something like these conditional probabilities that an expression y is a continuation of some smaller expression x. Now, you could just say, oh yeah, let's just, tack that on in some ad hoc way. And maybe you might get something from that. But I think what's really nice is that this intuitive way of decorating substring containments with the probabilities, which are those approximated by language models, fits perfectly into existing theory in category theory, an existing framework in category theory that mathematicians have been working with already. And that's what I referred to as enriched category theory earlier. This gives a little bit of evidence that this kind of mathematical way of thinking might be fruitful in exploring some things in language. You start with something really simple, and then what do you get from this? So it turns out you get a lot. Now I'm not going to go through each of these things, but I just want to give you a teaser. Because you now have this whole toolbox of category theoretical ideas, you can actually get pretty far with this idea of language as a category sort of enriched over probabilities. And one thing that my co-authors and I do, we kind of go through this toolbox and say, oh, what does this idea in category theory look like in this context of language? And so it turns out there's a way to represent meanings of expressions sort of in the tradition of the distributional hypothesis that I mentioned earlier. Category theory also gives you a way to operate on those representations, a way to kind of create different concepts given elementary ones, sort of as building blocks. And these operations are akin to logical operations, and so you have some interesting connections to logic there. And you can do that before you even incorporate probabilities, actually, so it's a nice proof of concept. But the mathematics is so nice such that when you do incorporate probabilities in the way we described, you can actually represent these meanings again, and you can actually operate on these representations in a way that, again, fits this logical perspective. And so there's some nice consistency there. And then it also turns out there's a really interesting way to map your whole story, everything we've talked about, expressions and language and the conditional probabilities of their extensions, map all of that discussion to a more geometric perspective. So here's what I mean. Given two expressions in language, there's sort of a probability in between them. The probability that given an input or a prompt like blue, the continuation of it is going to be something like blue marble. Given that probability, there's a way to get a distance from that number. How do you do that? Well, that's what we talk about in these papers that I'm mentioning. But when you transfer from you shift your perspective from probabilities to distances, now it turns out there's a way to view language, expressions in language, as something like a metric space. In this perspective, words that are likely continuations of your input or your prompt are close to the prompt. And words that are not extensions of it are infinitely far away. So from my picture here, blue and blue marble are close together because, there's some non-zero probability that blue marble is going to be an extension of the word blue. But blue is not contained in the expression curiosity killed the cat. So that expression is sort of infinitely far away from this word we're starting with. Now, this is an interesting shift in point of view because you kind of have a metric space, but you don't necessarily have symmetry. So the distance from blue to blue marble is not going to be the distance from blue marble to blue because blue marble is not a substring of blue, so you can kind of see how they're not symmetric. But you don't just toss out metric space theory out the window. You get what mathematicians call a generalized metric space. So you have a metric and it satisfies this triangle inequality, which actually is like this composition rule in category theory. And there's lots of things you can do now with generalized metric spaces. There's different avenues you can explore, but the paper I mentioned at the very beginning, joint work with Juan Pablo Vigneaux, we explore an idea called magnitude. Magnitude is a numerical invariant that you can associate to a metric space. It effectively captures the number of points in your metric space. It's related to the cardinality of sets. It's related to the Euler characteristic of topological spaces, if you're familiar with those ideas. In fact, there's a way to kind of recover these familiar ideas from this idea of magnitude. And so we take this existing theory that other mathematicians have explored and developed, and we say, what does this existing theory look like in the context of language? In other words, what is the magnitude? What is this number associated to this category of language enriched over these distances, this generalized metric space of language? So you can look at magnitude and get a number. There's a way to kind of rescale a metric space by introducing some parameter t. So when you introduce this parameter and look at rescaling, you actually get a magnitude function, not just a number. If you pick your parameter, then you get a number. So we work out all of this, all of the details. So Juan Pablo actually, in 2024, looked at a novel combinatorial way to compute magnitude. And so we apply his combinatorial method to our language setting. And we end up getting a function at the end, okay? This magnitude function associated to this category, this generalized metric space of language. And what's really interesting, I think, is that at the end of the day, this function involves a sum of Salas entropies associated to the probability distributions on your token set corresponding to each string, right? So if I input some string or some symbol into my language model, I get a probability distribution on the token set. It samples from that distribution. I tack that onto my string, and then I kind of feed it in. So these probability distributions associated to inputs, you can compute the Salas entropy of each distribution. And then if you add them all up, and then you add on another number at the end, which I won't get into here, this ends up being the magnitude function of our category. I think this is interesting for a number of reasons, one of which is that this result, in an interesting way, naturally combines ideas from category theory, from language, from topology too, because I mentioned magnitude is like an Euler characteristic, and then also ideas from information theory kind of pop out naturally at the end because of these Salas entropies. So I think it's an interesting blend of ideas. This is my high-level introduction to this work. Where can you learn more? So most of the theory behind enriched category theory of language, this is based off of joint work with John Torilla and Yannis Vlasopoulos back in 2022. So I've mentioned the paper at the top of the screen there. And the computation of magnitude and this idea of connecting the theory directly to a large language model, this is in our new preprint with Juan Pablo that was released on the archive in early 2025. So if you're interested, take a look at these papers. And as I mentioned at the beginning of this video, what I've shared today is just a little bit of a longer talk that I gave at the Institute of Pure and Applied Math at UCLA. So you can check out the talk there. And I hope you enjoy these ideas as much as I have.